see what Matroid does. And I'm going to talk about attacking computer vision for the purposes of telemedicine and teleophthalmology. So that needs an introduction to adversarial attacks in computer vision. We're going to look at some examples of real-life attacks and defenses outside of computer vision and, outside of medicine, outside of telemedicine and inside telemedicine. And then I'm going to issue a challenge to everyone on this call to come and attack Matroid for the purposes of making telemedicine more robust for everybody. So Matroid is a point-and-click tool that allows the ingest of images and video from a variety of different places, including medical imaging devices, as well as live videos from a variety of video cameras. So pretty much any enterprise video camera or any enterprise source of video can be connected to Matroid. And there we have a detection army that can annotate data, that can automatically create neural networks and deploy them to get real-time alerts, statistics for things that happen very frequently, and a visual search engine that allows searching of the past. So all that together usually means that someone who is not a programmer, maybe a doctor or someone who is an engineer who doesn't code in a factory, allows them to deploy computer vision products. So as to give you an overview of our deployment scale, Matroid has been deployed in advanced rocket car and general manufacturing facilities throughout the United States and the world. We're in every rocket factory, many advanced car factories. We're used by the US government. There's almost 100,000 video streams that are being analyzed by Matroid 24/7. We're 8 years old with more than 30 patents. So let's go live in the product very quickly. The product looks like this. So here I have a dashboard where I'm monitoring a variety of video streams. Bloomberg is a very complicated video stream that's always changing, so it's helpful to see it. There's a video player that has that is inherently got AI built into it. We were the first company to build computer vision into a video player that is used by non-programmers. So you can stop at any point, give feedback, and annotate and re-annotate things as necessary. This is not an airplane, so I'm going to remove that. But basically, by having the ability to seek to different objects in a video instead of just different times in a video, we've upgraded computer vision video players. And we did this 8 years ago, and since then we've been building nonstop. So there's a lot of features that let you obviously deploy computer vision and then start getting notifications. You can have bar charts and graphs and things like that. But then you can build detectors to deploy on video streams. So here I'm in the studio. I'm building a detector. In this case, I'm building a detector that's operating on fundus photos, and I'm building a segmenter. So this is basically annotating every single pixel with what it is, and then expecting that the machine learns from then on. So for example, maybe I want to annotate this area. So I put in a few clicks. So this is an advanced LLM that allows me to put in a few clicks, explain where I do want and where I don't want. And then now I have this area segmented out in order to learn in the future what this area looks like. And then when I hit this train detector button here, what will happen is we will try automatically everything that a typical Stanford trained machine learning engineer would do in order to build a neural network to then deploy it to operate on future images or future video live. And so that's sort of the super high level overview of the product. We have detectors all day long. We can detect hundreds of millions of things. We're deployed in many places. Yet another example is operating off of X-ray. So when you go through an airport, your luggage is typically scanned with an X-ray machine. And that X-ray machine is looking for prohibited items that you're not supposed to take on board, guns, knives, etc. And so here you can see the product basically analyzing how well a detector learned to detect guns and knives, and this inside X-rays. And so this is something that we can train even non-programmers to do, because you can still explain, things like a confusion matrix, so basically you can get a confusion matrix and then click through the confusion matrix to see where mistakes were made. This is all explainable to someone who isn't a programmer. So end to end, you have non-programming, and then you can deploy, get a dashboard, get analytics, statistics, etc. And that means a lot of doctors can use us, and that's really exciting. So let's go back to the slides and dive deeper here. So of course we discussed Matroid and the different deployment modes. So most importantly, this talk isn't just about computer vision. It's almost all of computer science. The entire computer science industry is reinventing itself around AI computations. So what's happening is all computing chips are reinventing themselves to accommodate primarily linear algebra operations. And they're doing that because most compute-intensive tasks are related to deep learning and machine learning these days. So new attacks are also arising. New attacks that are along the lines of buffer overflow attacks, for example, used to be a big way to attack computers in the past 70 years. They still are. And nowadays, there's a new mode of attacking AI and machine learning models that have been deployed. What is this attack? We're going to focus on computer vision for the sake of adversarial attacks, but in general, most models, even when they're not operating on images and video, maybe are operating on text, they can still be attacked. The attack mode has to be different. So for this talk, we're going to discuss image classification, but everything I'm going to say also it generalizes to non-image classification. So it generalizes to it generalizes to segmentation, object detection, where you're putting a bounding box. It generalizes to many other computer vision tasks. But for the sake of this, we're going to focus on classification. I give you an image. I ask, what is it? The model has to say what it is, maybe out of 1,000 different classes, exactly like ImageNet. So in this case, we run the image of a panda through the model. We say, and the model says this is a panda. I'm 57% confident. And then we add a little bit of noise. And then when we add this little bit of noise and we run it through the model again, the model says, oh, actually, I'm 99% confident that this is a gibbon, which is, of course, not correct. The model has been successfully attacked, and that's a problem. So these attacks have been around for a while. How do they apply to medicine, and how hard are they to thwart? And what's the problem to begin with? Well, let's say for X-ray, right? X-ray scanning at airports. You definitely don't want the X-ray scanner at the airport to be susceptible to adversarial attacks, because what if, say, a bad actor wants to bring a gun on board? All they have to do is also put an adversarial patch inside their luggage. And then when the luggage goes through the scanner, if it's an automatic scanner with a neural network, the neural network is full. It says, oh, this is regular clothes and luggage, let it go through. And then now we have a gun on board. That's a big problem. Another thing is that these adversarial attacks are often defenses. So you can think that, let's say it's a new world war or some problematic war situation. In that scenario, it would be excellent if you could have a patch on top of your house where any kind of drone or other sort of weapon that is using convolutional nets and neural nets in order to find its target just thinks, oh, this is actually a big open field, so that it doesn't drop its bomb or anything like that on your house. This would actually be a good defense. These kinds of defenses have actually been around for a long time. If you guys have ever seen fighter jets give off fireworks, it's not actually fireworks. It's flare and chaff coming out of an airplane in order to fool sensors on board missiles that are coming after the plane. So this is a very rudimentary, an old form of an adversarial attack that was used as a defense. So what happens is typically missiles are heat-seeking or they're metal-seeking. They seek metal using a radar, or they seek heat using infrared. These pellets give off heat, and they give off shards of metal that mimic the signature of an airplane. And then usually the airplane banks sharply and then gives off the chaff, so it looks like it's continuing in the same direction. So the hope is that a missile gets confused and goes after the fake decoy. This is an adversarial attack but is used as a defense. There's a long history of actually biological neural nets being used in this manner but we don't have time for that. So I'll put this in the slides, and I'll put the slides up. So in telemedicine, where would we see adversarial attacks in telemedicine? So obviously drugs are prescribed all the time in medicine, in telemedicine, and not just in ophthalmology, but everywhere in medicine, right? And if you could just fool a doctor into thinking you have a particular disease, then you get the medicine. And often insurance is forced to pay for it as well. So in this scenario where perhaps telemedicine or teleophthalmology is happening, if you couldn't fool the model that is being used to make the diagnosis, then you basically have the ability to get any drug you want. And that's a big problem, right? It is a problem that bad actors will go after. So this is one example. By the way, all the other previous examples, those are like very much serious examples, life or death. This is a little bit less life or death, but it is still a problem that needs to be resolved. Another one is basically if you actually have a disease, or if you are a bad actor that likes to sue doctors, you can go find someone that has a disease, get them to use your telemedicine tool. The telemedicine tool will say, oh, you don't have the disease. You obviously recruited someone who has the disease, maybe someone who has glaucoma. You get them in, and then you say, look, let's use this tool that the doctor put out online. And then you put an adversarial patch through it. The tool says you don't have glaucoma. And now you have a patient who is knows they have glaucoma, is being told by a doctor that they don't have glaucoma. So that's sort of the beginnings of a malpractice lawsuit. Again, this is an attacker. So they are being maximally adversarial here. It might sound like that this is like a really contrived example, but you are having problems with telemedicine that may very well put you out of practice, So this can be a big problem. So the question is, how do you generate these adversarial attacks? So you could say to yourself, look, I'm just going to hide my model from the world. I'm going to hide my data set. I'm going to hide my model. I'm going to hide everything. And therefore, there's no hope for an attacker to attack me. And so there is different modes of amount you can hide your model. You can say, look, I'm going to give everybody access to my architecture and weight. So my model is open source. In that scenario, obviously, you don't think you're going to be able to defend anything. And then you could say, oh, well, I'm going to hide my model, and then I'm going to just return a confidence score vector. So the model is hidden, and I'm just going to say, I think you have glaucoma with X probability, and you don't have glaucoma with Y probability, and that's it. In that case, you can still be attacked. So there exists attacks to do that. And again, my slides will have examples of how that attack can happen. So then you say, okay, I'm not even going to return the confidence score. I'm just going to say whether you have glaucoma or not. You can still be attacked in that case. So you're just getting the top one without a score. So you said, okay, fine. Then I'm only going to let the patient use my model once. They're going to get one try so that they don't like fuss around with my model trying to fool it. So you only get the top one, and you get a very limited number of tries, maybe just 4 or 5 tries. You still can be attacked. And then it's 4 or 5 tries. And then even if you get just one try, you can still be attacked. So this is insane. It's really bad news. Unfortunately, all of these attacks are variants of the fast gradient sign method. Happy to talk to anyone about it in depth. I'm going to leave the slides here. I have just 15 minutes for the slides. We'll go into depth here, and I have other talks that go into depth here. So basically, the problem is that if you have an attack for logistic regression, it typically transfers to decision trees. So if I build an attack for logistic regression, I can use that attack for decision trees in other models. I also have a problem with cross data set transfer. Let's say I fix the model. Let's say I fix logistic regression, and I do I train logistic regression on one data set for glaucoma, and then a different data set for glaucoma. My adversarial attack for the first data set for glaucoma will probably transfer to the second one as well. And if I train an adversarial attack for an ensemble of models, so you have one model, this model is made up of a neural network plus logistic regression plus SVM plus decision tree plus a bunch of other models, and then I build an attack, or I build build an attack for that ensemble. That attack will actually be really good at fooling any single member of the ensemble. So then it becomes a really strong attack that can break many of the hidden models that we mentioned before. This all happens because these models are linear in the input. So if you think about a neural network's training is not linear because it's typically many matrices multiplied together, and the weights that you're training are inside those matrices. But if you keep those weights fixed, what happens is a neural network is typically a bunch of matrices multiplied together with some nonlinear activations, but all those are just multiplied in by 1x, which is the input. And that x is usually shows up in a linear manner. So what happens is a method like adversarial fast gradient sign can rapidly find a place where your model is fooled, and then it can also rapidly get into a regime where your model is fooled confidently. So it says, I'm 99% sure that this is a gibbon instead of a panda. So, you can change the architecture so that the input is not linear in the input. Sorry, the model is not linear in the input. And that does work quite well. For example, a deep RBF network or some variants of vision transformers, but those are still foolable. You can still fool both of those networks, so it's not enough. You still have to do more. And Matroid as a company, we've become hardened to these attacks over a long period of time. So we've been doing these attacks. And what I'd like to leave you with is a challenge, basically. Please come and attack us. We basically give you a challenge as an image of, in the image there's a scene. And all I ask is that we give you an API access, and you can actually call Matroid many times. You can call the API thousands of times. So this is a pretty permissive scenario. In that scenario, if you manage to fool the network, we have $15,000 prizes. And of course, we would love to offer you a job offer as well. But more importantly, we'll just pay you. We'll straight up pay you if you can attack us. And that will help everybody. It will help doctors who are offering telemedicine. It will help airports who are trying to keep planes safe, and it will help in general the robustness of software that is deployed out there. Thank you so much for your time. Really appreciate it. Hope to see you guys at the next App Plus. Have a good day.